Hey everyone, and welcome. Today we're going to talk about something absolutely tiny, but with a ridiculously huge impact. I'm talking about the bipolar junction transistor, the BJT. This little guy is pretty much the foundation of all modern electronics, so let's get in there and see what makes it tick.
All right, to really kick things off, check out this idea. One of our sources actually compares transistors to, get this, brain cells. And you know what? That's not really an exaggeration at all. Think about it. There are literally billions of these little switches firing away inside your phone, inside your computer, making all that digital magic happen.
So, what's actually inside one of these electronic brain cells? Let's take a look at the blueprint.
Okay, so at its heart, a BJT is basically this three-layer semiconductor sandwich, and it comes in two main flavors. First, you've got the NPN type. That's where you have a thin slice of P-type material squished between two N-type layers. Then you've got its opposite, the PNP, which is, you guessed it, an N-type layer sandwiched between two P-type layers.
Now this is where it gets really interesting. How these three layers, the emitter, base, and collector, are actually designed. The emitter's whole job is to emit or supply the charge carriers, so it's heavily doped. Doping just means they've mixed in some impurities to get a whole bunch of charge carriers ready to go. The collector, well, its job is to collect all those carriers, so it's physically the biggest of the three. And then, smack in the middle, you have the base. This is the key. It's super thin and only lightly doped, and that, as you're about to see, is the secret to the whole thing.
All right, so we know what it's made of, but how does this thing actually work? Let's dive into the engine room, and we'll use the NPN transistor as our example, because it's the most common one out there.
Okay, before we go any further, there are two key terms we gotta know: forward bias and reverse bias. Think of forward bias as flipping a switch to on. You apply a voltage, then boom, the gate is open, current flows easily. Reverse bias is the opposite. It's flipping the switch to off. You apply voltage the other way, and the gate slams shut, restricting the current. These are basically the on-off switches we use to control the transistor.
All right, let's see this in action. To get the transistor into what's called its active mode, we start by applying a forward bias to that emitter-base junction. Remember, that's the on switch. As soon as we do that, a whole flood of electrons gets pushed from the emitter right into the base.
But here's the clever part. Remember how that base is super thin and doesn't have many charge carriers of its own? Well, because of that, only a tiny, tiny fraction of those electrons, we're talking like 5%, actually find something to combine with. This creates a really small current called the base current.
So what happens to the other 95%? Well, they shoot right past the base and get sucked up by the collector, which is reverse biased and acts like a powerful vacuum cleaner, just pulling them all in.
And that creates a huge flow of current, the collector current. And that right there is the magic trick. You have this tiny little trickle of current going into the base, and it's controlling a massive river of current flowing through the collector. A tiny input signal creates a huge output signal. In a word, amplification.
So that's amplification. Pretty cool, right? But that's just one of the things a transistor can do. By playing with the forward and reverse bias on its junctions, we can unlock 4 totally different operational modes. Let's check out the control panel.
So here they are, the 4 modes. We've already talked about active mode. That's our amplifier. But what if we forward bias both junctions? Well, then you get saturation mode, which is basically a fully on switch. And if you reverse bias both, you get cutoff mode, a completely off switch. Now there's a 4th one, reverse active, but it's not used very often, so we're really going to focus on these big 3, active, saturation, and cutoff. To make this all a bit easier to picture, let's use an analogy. Just think of a transistor as a super precise digital water faucet.
It's actually a perfect way to think about it. Cutoff mode, that's the faucet being completely off. Not a drop of water or current is flowing. Saturation mode, that's the faucet cranked all the way open, full blast. And active mode, that's where you get to be really precise, carefully turning the knob to control the flow from a tiny trickle all the way to a steady stream. That's your amplifier.
Okay, we've got the mechanics, we've got the modes. Now, let's do a quick face-off between our 2 main players, the NPN and the PNP transistor. When you put them side by side, you'll see they're pretty much mirror images of each other. A neat little trick for the symbol. For NPN, the arrow is not pointing in, so it points out from the base. For PNP, it points in. The main charge carriers are different too.
It's electrons for NPN and things called holes for PNP. And because of that fundamental difference, everything else is flipped. The voltages you need to apply, the direction the current flows, it's all the exact opposite.
So the big question is, why do you see NPN transistors everywhere? I mean, they're way more common. Well, it really just comes down to physics. The electrons in an NPN transistor are just, well, zippier. They have higher mobility, which means they can move through the material much faster and more easily than the holes in a PNP. This makes NPN transistors faster, more efficient, and, big bonus, they usually end up being cheaper to make.
Okay, we've gone through the structure, how it works, the different modes, the two types, but let's zoom out. So what? Why does this tiny little component matter so much in the real world?
Really, it all comes down to those two amazing functions we talked about. First, as an amplifier, it can take a super weak signal, say from a radio antenna or a microphone, and boost it up into something we can actually hear and use. And second, as an unbelievably fast electronic switch. By flipping between that on saturation state and the off cutoff state, it creates the ones and zeros, the binary language that is the absolute bedrock of every single digital computer.
I mean, think about it. From the very first transistor radios all the way to the supercomputer you carry around in your pocket, this one little component's ability to amplify and switch has completely redefined our world. It really is a tiny giant. So it leaves you wondering, right? If this is what today's microscopic brain cell can do, what's the next one going to make possible?